In a linear system of equations, we've managed to convince ourselves that the number of variables tells me the dimension of the space in which the solution set is going to live. The number of equations in the system tells me the number of hyperplanes that I'm going to try to intersect to make that solution set. And by looking at some 2x2 simple examples, we're also beginning to understand that the number of pivots in a linear system tells us how many of those equations are telling their own unique, independent of each other story. And to explore that a little bit further, let's push from 2 dimensions up into 3 and look at how this story plays out with some 3x3 linear systems. Remember that there's a story to be told both by thinking about columns, i.e. variables, and by rows, i.e. equations or hyperplanes. In the column viewpoint, those columns in a linear system that have pivots correspond to the basic variables. Those are the variables whose values are actually determined by the system and not by the whims of the universe. And so those are going to be the variables that I'm going to say matter in a way in the solution set, right? Those for which the values are determined by the system. And that's one thing that the number of pivots tells us, right? How many variables have their values determined by the system. On the other hand, if we take the rows viewpoint, every pivot column also corresponds to a pivot row. Every pivot is both the only pivot in its row and the only pivot in its column. And so the pivot rows are going to tell us a story about how many equations, how many hyperplanes are independent from one another. How many equations are each telling their own essential and independent story that helps us to find the solution set. And so the number of pivots really tells us both of those things. And let's see a little bit more about how that plays out in a 3x3 case. So let's suppose that I have a 3x3 linear system, I do the row reduction on it, and I find out that it has 3 pivots. And so its reduced row echelon form of its augmented matrix will look something like this, right? A pivot in each of the first 3 columns over here would mean that each of the variables, let's say x, y, and z, all have their values determined by the system, and that there are no variables whose values are determined by the whim of a free choice in the universe, right? What that's going to tell me is that the 3 hyperplanes, which since we're now in 3 space, hyperplanes are actually 2-dimensional planes sitting inside of 3-dimensional space, right? The 3 hyperplanes that determine our system are each going to intersect at a common point. This visual from the great immersive math free online textbook helps us to appreciate what the geometry of that actually looks like. So here's 3 planes arranged inside of a 3-dimensional space. Each pair of those planes, let's say I take this one and that one, is going to intersect. As long as they're not parallel, that pair of planes is going to intersect along a line. And because I have 3 planes here, there are 3 pairwise intersections, giving me 3 lines, and those 3 lines all come together at a common point in this example. So this is the arrangement of the hyperplanes in the case where I end up with 3 pivots, right? That the 3 hyperplanes intersect at a single point inside a space, and so my system has a unique solution. So in the rows viewpoint, my 3 pivots, my pivot rows, tell me that all 3 of my hyperplanes matter. They all tell a unique independent story that the others do not. And so they intersect in a single point. That means that my system is consistent. It has solutions. There's at least one x, y, and z that solve this system. But also that the solution of that system is unique. There is one and only one point at which all 3 of these planes come together and intersect. And so that's, in a sense, what we might think of as the ideal situation for a 3x3 system. The ideal situation is one in which we have a unique solution, that there's only a single x, y, and z which satisfy all 3 of our equations simultaneously. And when we have 3 pivots in a 3x3 system, that's what happens. So what happens if a 3x3 system has fewer than 3 pivots? Suppose for the moment that the reduced row echelon form looks like this. So I end up with a pivot in row 1 and a pivot in row 2, equivalently a pivot in column 1 and a pivot in column 2, but I end up with no pivot in row 3, and for that reason also here, no pivot in column 3. So what story is this telling? The fact that I have 2 pivots. Well, we could think of it from the rows viewpoint, that only 2 of the hyperplanes in my system are actually going to matter. Only 2 of them are telling their own story and helping me determine the solution set. And so the third one is redundant of the other two. The story that the third one tells is not independent. It's not essentially different from the story that the other two are telling me. Okay, so what does that mean more specifically? For this system, it means that that third equation, that third row, after it's row reduced, gets all the way down to the equation which not only in this example has no non-zero entries to the left of the augment bar, but it also has a 0 on the right side of the augment bar. And so that third equation after row reduction turns into the equation which has no variables in it, and so the left-hand side is just 0, but also its right-hand side is 0. And so we get an equation which, even though it has no variables in it, it is nevertheless a true statement. 0 is equal to 0. And so what that means is that it's possible for me to have a solution for this system as long as the other rows, as long as row 1 and row 2, each determine hyperplanes that actually have a non-empty intersection with one another. So only 2 of my hyperplanes actually matter, and the third one doesn't screw us up. Right? The third row is not giving me something which is inconsistent and screwing up the ability for my system to satisfy all 3 equations at the same time. So what we're hoping is that this means that the system is going to be consistent. But consistent how? This visual from the Immersive Math website it gives a really good illustration of what this circumstance might look like. Here I have 3 planes, and none of my planes are parallel to any of my other planes, but the pairwise intersection of any 2 of my 3 planes is all the same line. So this plane and that plane come together in this line. That plane and that plane come together in the same line, and this plane and that plane come together in that same line. So here I have 3 planes which are each kind of telling a different story, but suppose that I were to remove one of them. Let's say I remove this plane that's kind of sitting horizontally. If I delete that plane from the system, the solution of that system is not going to change. That solution set still consists of all of the points along this black intersection line. And so there's the key. One of my hyperplanes is redundant. It's not telling its unique story, because if I were to take it out of the system altogether, my solution set wouldn't change at all. That's the tell, that's the giveaway for one of my equations not being independent of the others. So what I have is a system that has solutions. It's a consistent system, but it has a whole lot of different solutions. There are infinitely many different points that lie along this line, and any of those points will be a solution of all 3 of the equations in my system. So it's a consistent system, but it's a consistent system that has infinitely many, in particular a whole line's worth of solutions. So when I have 2 pivots, this is one thing that can happen, right? That I can still have a consistent system, but my system necessarily will have to have an infinite number of solutions in that case. Does that always happen if I have 2 pivots? Well, the important thing about this last example was the fact that my right-hand side in this third row was still 0, even after the left-hand side disappeared completely. If that were not to happen, let's say I did all my row reduction and the right-hand side of this bottom row ends up being 7, or something which is not 0. Then that's going to screw me up, because it's still going to tell me that only 2 of my hyperplanes are really going to matter to my solution. But that third equation, 0 is equal to 7, is not a true statement. That third equation can never be satisfied for any choice of x, y, and z. And therefore, there's no choice of x, y, and z which is going to satisfy all 3 of the equations in my original system. So even though only 2 of the hyperplanes matter, only 2 of my rows have pivots out of the 3, the third row, the one that doesn't, is a derelict, right? It's let us down. It completely ruins us, right? It ruins the possibility for the system to be consistent, because there's no way to satisfy that third equation with any choice of x, y, and z. So this system is inconsistent, and we'll say that it has no solution. Here's Immersive Maths Interactive for this particular situation. I have 3 planes, 3 hyperplanes, 3 equations. Only 2 of them really matter. Only 2 of them are pivot rows in my row echelon form for my matrix. But the third one ends up giving me an inconsistent answer, 0 equals 7 or something of the like, right? And so what's happening there is that I have 3 planes, and any pair of my planes is going to have a line of intersection. But my 3 planes together, the 3 of them don't meet at any point. This is kind of a higher dimensional analog of the situation in our 2x2 case, where we had 2 lines that were just parallel, right? They weren't telling a unique story from one another, and they happened not to intersect at all. So this is an illustration of that example in the 3x3 case. But this is not the only organization of three planes which has no solution. You might want to think about what a situation like this would look like. Let's suppose that I have three equations which give me hyperplanes, and all three of those are parallel to one another. How many pivots would you expect? What would you expect the reduced row echelon form of this system to look like? Or suppose that I have three equations that are giving me three planes, but two of those planes are actually right on top of one another. That's a special case of all three being parallel to one another, but it's still, my system is going to be inconsistent because there's no point at which all three of these planes come together. Now what would you expect the reduced row echelon form of this to look like? How many pivots would you expect to see in this system? So the point is that, at least in 3 dimensions, there's a variety of different ways for a system to look inconsistent. But they're all going to rely upon one or more of the three equations being redundant with the others, right? One or more of them telling a story that's not independent, not telling its own unique story to help us determine the solution set. And so these no solution cases are only possible when I have fewer than a full complement of pivots in my system, right? I have a missing pivot in those examples, at least one missing pivot. And so this is kind of leading us to the following conclusion to wrap it up, that pivots are an essential measurement of the independence in my system. To what extent does each of the variables in my system have its value determined by the system and not by a free unique choice of the universe? And how many of the equations in my system are each telling their own unique independent story to help us find the solution set? If we're able to maximize the number of pivots, then we're maximizing the unique independent contributions of each variable and each equation. And when I maximize the number of pivots, I can have unique solutions. When I don't maximize the number of pivots, I can have either solutions which have infinitely many points in them if we get really lucky, or possibly solutions that don't exist at all, inconsistent systems. Pivots are going to be an essential tool for us in measuring independence in linear algebra, and that's going to be one of the main themes of the questions we want to consider in our next chapter as we begin to put linear algebra on a firmer theoretical foundation.